Hi, in this video we're going to continue talking about digital electronics. This video bases on the previous one. We're going to continue talking about some basic circuits, and then in the later parts of this video we're going to try to do something useful with them. A demultiplexer IC is a combinatorial IC built from many different logic gates. The demultiplexer takes in one input value and sends it to one of many possible outputs. It can be used, for example, to calculate binary addition by choosing specific inputs with push buttons. In this part of the experiment, we used 4 push buttons as the inputs and 8 LED lights as the possible outputs. By trying all possible combinations of input values, it was possible to see the LED lights light up in each case shown to the corresponding values in decimal. When the LED lights were connected to the ground instead of the voltage source, the lights were turned on to begin with and turned off in the same order as they turned on in the first part. The 555 timer IC works as a clock, sending pulses in specific frequency. The frequency of these pulses is dependent on the capacitance of the capacitors connected to the IC in pin 6. So when the capacitance increased, the pulse frequency decreased. A 4-bit counter IC and a 7-segment display were used to keep track of these pulses. When a push button was connected to pin 2 of the 4-bit counter, it was possible to stop the numbers changing in the display by holding the button down, whereas when connected to pin 15, the numbers were reset to 0. In this part of the experiment, we used 4D flip-flops connected together to create a shift register. All these flip-flops were also connected to a LED light, showing their output values. We used the 555 timer IC from the previous part of the experiment to create continuous pulses and a push button to control these pulses. Pushing the button down for at least one clock pulse sent an input value of 1 to the first D flip-flop, which then carried it on to the other flip-flops in line. The input value changed to 0 as soon as the push button was released. The input values traveled as expected with small capacitors, for example with the capacitance of 4.7 microfarads. However, these lights seem to turn off 2 at a time when using the 100 microfarad capacitor, possibly because of background noise coming from the push button. We decided to use an SR latch between the push button and the first D flip-flop to minimize the noise. With this addition to the circuit, we could get the right kind of results for the 100 microfarad capacitor as well. In this part, we're going to try to build something useful using the things that we learned before. We're going to try to build a ECG, or an electrocardiograph. A ECG is used to measure the heart rate. We're going to use an infrared emitter and an infrared detector. Infrared light tends to scatter off hemoglobin, which means there will be more scattering when the heart pulses, meaning there will be more infrared light that will go into the detector. The main circuit is actually quite simple, only having 5 components. But the output signal is unfortunately way too small and has way too much noise in it, so we have to add some additional components. We can use a capacitor to filter out the high frequencies of the signal, and then use an operational amplifier to boost the signal. And that parallel to a capacitor can be used to filter out the lower frequencies. Then we connect that to a potentiometer to be able to control the output signal, and then repeat the filtering and amplification process again. Then we finally have something that is readable. Then just to test it, we connect it to an LAT and we were able to see some results. And then we connected it all together and we were able to count the number of pulses. And then doing some calculation, we were able to find out the beats per minute. Now we recorded the data live through something called a red spark. As you can clearly see, this is a pulse. Unfortunately, it adds a few pulses here and there and it skips a few, but overall it tends to have the correct number. If you've seen a cardiograph before, you realize it looks nothing like this. The main reason for that is something called clipping. The operational amplifiers only provide maximum of 5 volts, and we amplified the signal more than the amplifiers could handle. This is a well-known case in audio. When somebody turns the gain way up and talks way too loudly, he'll probably get something that sounds like this. But since we're only looking for the number of beats and not how the beats look like, this is okay. Now that we have it working, mostly, it's time to do some testing. Now, unfortunately, we didn't have any test animals to test it on, but we had the next best thing, humans. We took the pulse of 3 individuals for 15 seconds and then made them put their hands in ice for 2 minutes. Then we measured it again and saw if there was any change. Now, from our tests, we found that the heart rate went considerably down. But this was, of course, just one test. Now, we were supposed to do a similar, but not the same experiment again, taking the pulse at the beginning and then make somebody do something and then take the pulse in the end. But we thought it might be nice to record the data live and then write an algorithm that finds the space between each pulse and see how that changes. We had a test which was holding our breath as long as we can. And it was then when we realized that we should never try anything new. Now, even though the heart rate, as I said earlier, was more or less correct, it skipped a few beats and it added some here and there. Now that really messes up the data. And we ended up making way too much noise. Now, we were able to use some algorithms to guess some trend, but I wouldn't take them too seriously. Now, that's all that we did this week. Have a nice day.